Hello everyone and welcome to the AP Bootcamp topic review. In this particular lesson, what we're going to do is we're going to review some of the topics that I won't necessarily have time to go over too much in depth throughout the year, but that you are expected to know. So first, we're going to begin with the basics of trigonometry, which if you took pre-calculus with me last year, a lot of these slides are going to seem very familiar. Now, trigonometry refers to the relationship between the triangle sides and their angles. Now, we're going to start off by reviewing the three basic trigonometric functions, which is sine, cosine, and tangent. As a reminder, sine is when you take the ratio of the opposite side with the hypotenuse. The cosine is the ratio of the adjacent side over the hypotenuse. And the tangent is the opposite side over the adjacent. So here we have a right triangle, and just so that we understand what sides are what. Now, depending on where the angle lies, that's how we can identify what is the opposite and what is the adjacent side. The opposite side is always the side that is directly across from the angle. So that's why this side here is labeled as the opposite. The adjacent is the side that is next to the angle that is not the hypotenuse. So what's the difference between these two? The hypotenuse is always the longest side of the triangle. And if your triangle is on one of its legs, then that means it's usually the diagonal side. Adjacent, as we learn in geometry, means next to, and that's why it's this side, the one that is directly next to the angle. Now here I put SOHCAHTOA, which kind of helps us to remember what the ratios are for each of these trigonometric functions. So stands for S is for sine, O for opposite over hypotenuse, cosine, adjacent hypotenuse, and TOA, T for tangent, opposite over adjacent. So this little anagram here can help us remember what these trigonometric functions are. So now we're going to look at this particular example. We have a triangle here with the side measurements given, and we're trying to figure out what is the sine of that particular angle. Now the sine of the angle, first we're going to label all of these sides according to where the angle is located. So here's my angle, the side that is directly across, this is the opposite. 7, as you can see, is the longest because it's longer than 2, it's longer than 4. So this is the hypotenuse. And notice how it's the diagonal of this triangle. And then 4, this is the side that is next to the angle. So this is the adjacent side. So sine of theta, which is the symbol we're using for the angles, is going to equal to the opposite, which is 2, over the hypotenuse, which is 7. So that is the sine of the angle. Now, along with sine, cosine, and tangent, we also have the reciprocal functions, which are cosecant, secant, and cotangent. Now, reciprocal just means that whatever the ratio was for sine, cosine, and tangent, you would just flip it. Now, it's important to know which of these trigonometric functions is the reciprocal of which of the original 3 trigonometric functions. So I have them here. Cosecant, which is denoted as CSC, is hypotenuse over the opposite, which is the reciprocal of sine. So cosecant and sine are reciprocals of each other. Secant, denoted as SEC, is the hypotenuse over the adjacent, which is the reciprocal of cosine. And cotangent, it's got tangent in the name, so it's easier to remember that cotangent would be the reciprocal of tangent. So that means instead of opposite over adjacent, it's adjacent over the opposite. Now, additionally, we also need to keep in mind what are the quotient functions of trigonometry. Tangent is equal to the sine divided by the cosine. So that's a nice little identity to remember. And cotangent, since it's the reciprocal of tangent, instead of sine over cosine, when you flip it, it's cosine over sine. So just keep these in mind at a later time. Now we're going to see how to apply this and see if we can find these ratios based on this triangle. So first, we're going to go ahead and label these sides. My angle is down here, so the side that is directly across from the angle, this is the opposite side. 8 is the longest, so that means it is the hypotenuse, which is also the diagonal. And then 3 is next to the angle, so this is the adjacent. Now remember that secant here, if I want to find secant, secant is the reciprocal of cosine. So you can think about this as, okay, cosine is adjacent over hypotenuse. So the reciprocal would be the hypotenuse over the adjacent. Or you can find the cosine and then flip that fraction. Either way, you would get the same answer. So the secant of theta is going to be the hypotenuse, which is 8, over the adjacent, which is 3. And see, if I were to try to find the cosine, cosine is adjacent over hypotenuse, so 3 over 8. And if I flip it, I would get the 8 over 3. So whichever way you choose to think about it is fine. Now cotangent of theta. Cotangent is the reciprocal of tangent. So instead of opposite over adjacent, the cotangent would be the adjacent over the opposite. So I look at my sides here. The adjacent is 3 and the opposite is 5. So this is the cotangent of the angle. Now if we were to use the quotient functions to try to figure out what is cotangent, we could do that as well, right? Cotangent is equal to the cosine over the sine. And again, this is a bit of a longer way to figure it out, but just so you can see how it works. Cosine we had gotten here was 3 over 8. Sine is opposite over hypotenuse, so the sine would be 5 over 8, opposite hypotenuse. And when we have a fraction divided by a fraction, remember that we copy, change, flip. So this is 3 over 8, we're copying, we're changing to multiplication, and we're flipping, so 8 over 5. The 8s would cancel, and I'm left with 3 over 5. And you see that we end up with the same answer as here. So that's why cotangent is also cosine divided by sine. We would get the same thing. Now in trigonometry, we also discussed the unit circle. The unit circle is very important throughout this course, so we do need to know how the unit circle works, and additionally, you will need to have these values memorized. The good thing is here that we are never going to use degree measures, so we can just ignore this entirely. In calculus, we are only going to use the radian measures, which is these fractions here. As a reminder, radians are just another way of expressing an angle measurement. So it's like another unit of measurement for angles. Just like for length, we have feet, meters, inches, centimeters, etc. For radians, we have degrees. For angles, we have radians and we have degrees. So in calculus, we only use radians. Now let's review how this unit circle is structured. I know it looks very overwhelming, but there are a lot of patterns to this unit circle. First of all, the unit circle starts here at the positive x-axis, and then it goes around in a circle in the counterclockwise direction. The more you open towards the counterclockwise direction, meaning toward up and left, your angles are getting bigger and bigger and bigger until you make a full revolution. So here in quadrant 1, you'll see your radian measures starts with pi over 6, pi over 4, pi over 3, and then once we get to 90 degrees, the equivalent is pi over 2. Now I know that it's been a while, so as a reminder, a full revolution is equal to 2 pi. 2 pi is the equivalent of 360 degrees. Now, since there are 4 quadrants, if you divide 2 pi by 4, right, that gives us that pi over 2, right? Because if you put 2 pi over 4 and you simplify, you get pi over 2. So this is why that's 90 degrees. If you add another pi over 2, you get 2 pi over 2. which gives you pi. So that's why when you do another 90 degrees, or when you move to the next quadrant, that's why here it's pi. And if you add another pi over 2, you get 3 pi over 2. Add another pi over 2, you get 2 pi. So right here at the positive x-axis, this is both 0 and 2 pi. Now you'll also see these coordinates here. Now these coordinates are very useful because the x value, as I put here in this box, is equal to the cosine of that angle. So you don't necessarily have to worry about any triangles or anything like that. If I wanted to find what is the cosine of the angle pi over 6, I would look at the x and it would tell me it's the square root of 3 over 2. And the y here is the sine of the angle. So again, if I'm sticking with pi over 6, if I want to know what is the sine of pi over 6, it would be 1/2. Now, let's see if we can establish some patterns for these radian measures. Because, like I said, you do have to know what angles lie in what quadrant. You need to know this unit circle. Now, this doesn't necessarily mean that you need to memorize the entire thing, but if you at least know quadrant 1, you'll be able to figure out the rest of the cosine and sines for the other angles just based on the quadrants. Because if you look at these numbers here, let's stick with the pi over 6, the actual x and y value with anything, any radian measure that has a denominator of 6 has the same exact numbers. See, if I go here in quadrant 2, the cosine is square root of 3 over 2, sine is 1/2. We get the same numbers here. In quadrant 3, again, these same exact numbers. And in quadrant 4, same thing. The only thing that you notice changes are the signs, and we'll get into that in a moment. So first, let's look at these patterns for the radian measures. In quadrant 1, as you notice for these radians, the numerator is always just pi. So that's how you know an angle is located in quadrant 1. If I tell you what is the sine of pi over 4, you'll be like, okay, pi over 4 is in quadrant 1, therefore the measurement must be square root of 2 over 2, etc. If I go to quadrant 2, if you compare the numerator with the denominator, you'll notice that the numerator number is 1 less than the denominator. So 2 over 3, 3 over 4, 5 over 6. 5 is 1 less than 6, 3 is 1 less than 4, etc. So the numerator is 1 less than the denominator. By contrast, in quadrant 3, the numerator, you'll notice, is 1 more than the denominators. See, 7 is 1 more than 6, 5 is 1 more than 4, and 4 is 1 more than 3. So the numerator is 1 more than the denominator. Once you're in quadrant 4, this pattern may be a little bit harder to distinguish, but you'll notice that if I were to double the denominator and then subtract 1, I would get the numerator. See, 5 pi over 3. The double of 3 is 6, minus 1 is 5. The double of 4 is 8, minus 1 is 7. And the double of 6 is 12, minus 1 is 11. So here the numerator is double the denominator minus 1. So that's how we know where our angles lie depending on the quadrant. Now again, why do we do this? Why do I need to know what quadrant my angle is located? And this is to figure out the sine of the trigonometric value. And when I say sine here, I don't mean sine as in SOHCAHTOA. I mean sine as whether it's positive or negative. So that's what you see here, the ASTC, which what I said in class in pre-cal was that you can in order to help you remember, you can use all students take calculus. So to help you remember the order. A stands for all trigonometric functions are positive. So no matter what trigonometric function you're looking for, if you know that the angle is in quadrant 1, that means that both cosine, sine, also tangent, cotangent, secant, cosecant will be positive in quadrant 1. If your angle is located in quadrant 2, S stands for sine. So only sine will be positive as well as its reciprocal function, which the reciprocal of sine is cosecant. So only sine and cosecant will be positive. So if you know that your angle is located in quadrant 2 and I asked you for tangent, the tangent would have to be negative because only sine and cosecant are positive in quadrant 2. Quadrant 3, T stands for tangent. So if tangent is positive, then cotangent must be positive as well. And finally, C in quadrant 4 stands for cosine. So if cosine is positive, then its reciprocal secant must also be positive. So that's why we try to remember what quadrant our angles are in, so we know exactly whether our trig function will be positive or negative. Now, just to make sure that we know how to read the unit circle, we're going to evaluate for these two values. So first, we want to figure out the sine of pi over 3. Remember that sine is the y value. So I'm going to find pi over 3. This must be in quadrant 1 since the numerator is just pi. Here's pi over 3, quadrant 1. And sine is the y value. So that means the square root of 3 over 2. So this would be the sine of pi over 3. Now the secant of 7 pi over 4. 7 over 4, this part here, this indicates this is in quadrant 4 because 7 is double the denominator minus 1. So here are my values. Secant is the reciprocal of cosine. So therefore, I look at the cosine value and I flip it. So the secant of 7 pi over 4 is 2 over the square root of 2. Now, if you had me in pre-cal or even in algebra 2, we learned that you cannot have a radical in the denominator, so you would have to rationalize. So we're going to do that now. So I'm going to rationalize, and we do that by multiplying whatever radical is in the denominator to both the numerator and the denominator. So we're going to do the square root of 2 over the square root of 2. And we get 2 over square root of 2 over 2, and the 2's would cancel, which gives me a final answer of square root of 2. Now, in AP Calculus, you don't necessarily need to rationalize every single time, and this is because they're not testing you on your algebra skills. They're testing you on your calculus skills. So they're skipping a lot of certain steps because it's kind of unnecessary in terms of showing that you understand the actual calculus concept. So sometimes we'll rationalize because we'll need to for multiple choice questions to be able to identify the correct answer. But if this was a free response question, you wouldn't necessarily need to rationalize. You can leave your answer just like this. But we're going to practice both anyway, so that way you'll know how to identify both the rationalized version and the non-rationalized version, because really it's the same exact answer. So now let's continue with trig, and we're going to learn how to evaluate for these trigonometric values using what's called a reference angle. Now, a reference angle is any acute angle whose trigonometric values are the same as the angle that you are asked to evaluate for. So that's kind of what I was talking about here. Like I said, anything that has a denominator of 6 has the exact same values, except the signs may change, whether it's positive or negative. So if I asked you to find the cosine of 7 pi over 6, I know that it's the same exact number as pi over 6, which is the square root of 3 over 2, but it may be a different sign. So a little shortcut here when we're trying to figure out what is the reference angle, I put here as an example, if we have the angle 13 pi over 6, the reference angle would be pi over 6. So you just basically, for the reference angle of your radians, the numerator will always just be pi and the denominator is the same as the original angle. So let's try this out. I put here steps on how to evaluate for any of these trigonometric values. First, we're going to figure out what quadrant the angle lies in and also the sign of the trigonometric function that we are trying to evaluate for. So here my angle is 2 pi over 3. The numerator is 1 less than the denominator, so remembering our patterns here, this must mean that the angle is located in quadrant 2. Now, if we remember, right, A, S, T, C, all students take calculus. In quadrant 2, only sine and cosecant will be positive. So that means that the cotangent of 2 pi over 3 is going to end up being negative. Now, the second step is to find the associated reference angle, which we denote as theta prime. So this is my reference angle, which is pi over, and then the denominator, 3. So now we've finished step 2. Now, step 3 is to find the function value for theta prime. That means that we are going to find the cotangent of pi over 3. This is why I said that you have to know your unit circle, or rather know quadrant 1 by heart, because the cotangent of pi over 3 is the cosine of pi over 3 divided by the sine of pi over 3. Remember that cotangent is a quotient function. Yes, we can do, SOHCAHTOA and figure it out that way, but cotangent and tangent is also when you divide sine and cosine, and cotangent is when you divide cosine over sine. So if I wanted to know what is the cotangent of pi over 3, if you know your quadrant 1 of the unit circle, you don't need to look back. But if you don't, for the purposes of this lesson, I'm going to refer to the unit circle. I'm going to come back here a second. Here's pi over 3. Cosine is 1/2 and sine is square root of 3 over 2. So the cosine is 1/2 and the sine is the square root of 3 over 2. We have a fraction divided by a fraction, so we're going to copy, change, flip. So 1/2 times 2 over the square root of 3. Here the 2's will cancel and we get 1 over square root of 3. Remembering that we don't necessarily need to rationalize, but if this was a multiple choice question, they would have the rationalized version as an answer versus this one. So we're going to rationalize by multiplying the square root of 3 over the square root of 3, and that gives me the square root of 3 over 3. So this is the cotangent of pi over 3. It's not our final answer. The final answer, which we're looking for, is the cotangent of 2 pi over 3. Remember, the actual numeric number does not change. So what we do is we take the sign that we noted in the beginning, which is negative, and the number square root of 3 over 3. So this would be my final answer. The cotangent of 2 pi over 3 is negative square root of 3 over 3. Let's try that again with this one here. We want to find the value of the cosine of 7 pi over 4. So first, let's distinguish what quadrant this is in. 7 over 4, 7 is double the denominator, minus 1. So that must mean that this is located in quadrant 4. Now we need to figure out what sign, whether cosine, is positive or negative. So again, looking here at my quadrants, this is quadrant 4. C is capitalized, so that means that cosine is positive. So my final answer will be a positive number. Our reference angle is going to be pi over the denominator, which is 4. So pi over 4. So now I'm going to find what is the cosine of pi over 4. If I look back at my unit circle, Now, anything over 4, what's nice is that cosine and sine are the exact same values, which is the square root of 3 over 2. Square root of 2 over 2 and square root of 2 over 2 for both cosine and sine. So the cosine of pi over 4 is the square root of 2 over 2. But for my final answer, we are asked to evaluate for the cosine of 7 pi over 4. Like I said, we have to take the sign that we noted, so it's positive, and the number that we found, so it's positive square root of 2 over 2. So this would be my final answer. Now that we've reviewed how to find trigonometric values of any angle, we're going to go over inverse trigonometric functions. And this is helpful when we're trying to solve a trigonometric equation. Now, you won't really see too many of these, but it's always good to review just in case we do. The inverse of a trigonometric function means that we're going backwards. So I have here in green, if the sine of theta is equal to x, remember theta represents the angle and x represents a side or anything else, then the inverse of sine of that side ratio is going to equal to the angle. So and I put here in blue, we only use the inverse trigonometric functions when you're looking for an angle measure. Now, in order to be able to solve these equations, you need to know the unit circle. But just like before, right now, we're going to continue referring to our unit circle until you get that quadrant 1 memorized. So like I said, these inverse trigonometric functions are helpful when we're solving a trigonometric equation. So let's try this out. In order to solve a trigonometric equation, what your goal should be at the very beginning is to isolate the trigonometric function, meaning here in A, we want to get sine of x by itself. So we're going to subtract this 2 sine x over to the other side. So that way we can combine, because these are like terms. So 4 sine x minus 2 sine x is 2 sine x. And that's going to equal to the square root of 2. Now we divide by 2. So now what I have is the sine of x is equal to the square root of 2 over 2. We have our trig function here isolated. Now, in order to solve for x, which is our goal here, okay, we can't just, let's say, divide sine. It's not being multiplied. These functions here, or sine of x is attached. In order to be able to detach the sine and get the x alone, you need to apply the inverse operation of sine. And the inverse operation of sine is the inverse of sine. So x is going to equal to the inverse sine of the square root of 2 over 2. Essentially, what I've done is I applied the inverse to both sides, so that way it cancels out here and we get x by itself. Now, what this essentially means is that x is equal to the angle that would give me a sine of square root of 2 over 2. So that's what the inverses mean. We're looking for, instead of the ratio like we did before, we're looking for the angle that gives you the ratio that is inside of the inverse. For all trigonometric functions, when you're trying to solve for the inverse, most of the time on the unit circle, you'll have 2 answers, and that's okay. And that's because the sine of whatever angle that gives you square root of 2 over 2 occurs twice. You will get that sine is positive 2 times. So we're going to look here on my unit circle and looking at all of the sine values and see which ones equal to the square root of 2 over 2. So we have this one here, which is pi over 4. And over here, which is 3 pi over 4. So these are my 2 answers. And these are the only 2 answers because if you look at the other sine values, yes, this is square root of 2 over 2, but it's negative. So this is not the answer. And then same thing here. Here it's negative, so that's not the answer either. So that's how you can distinguish. Let's try that again with this particular question. We have the cosine of x plus the square root of 3 is equal to negative cosine of x. So we want to get cosine by itself. You can either subtract this cosine over here, or you can add the cosine over there, whichever way, it does not matter. I'm going to choose to subtract cosine of x from here, so that way it's one less step for me to do later. And we get that square root of 3 is equal to negative 2 cosine of x, since these are both negative. Now again, we want to get cosine alone, so we're going to divide by negative 2 to both sides. And we get that cosine of x is equal to negative square root of 3 over 2. Remember that it does not matter where I put this negative, it means that the entire fraction here is negative, and that's what I'm indicating here. So now to solve for x, in order to isolate it, we need to apply the inverse of cosine to both sides. So x is equal to the inverse cosine of negative square root of 3 over 2. So now we're going to look at our unit circle and see when the x value, because x is cosine, is negative square root of 3 over 2. Can't be in quadrant 1 because quadrant 1 everything is positive. In quadrant 2 we have here negative square root of 3 over 2, so 5 pi over 6 is an answer. In quadrant 3 we have 7 pi over 6 is my second answer. And then in quadrant 4, just to make sure, in quadrant 4 it is positive, so that's why that is not an answer. So these are my two answers. So that's basically everything that we need to remember for trigonometric functions. Know your unit circle or quadrant 1, know what inverse trigonometric functions are, and how to find those trigonometric values. Let's move on to our next topic, which is natural logarithms and the common base e. In order to understand what are natural logarithms and what e is, we need to understand what an exponential function is. An exponential function is any function where the variable is expressed as the exponent of the base. So I put here as examples, we have 5 raised to the x is equal to 25, and 3 raised to the 2x plus 1 is equal to 38. Notice how x is in the exponent. So this is an exponential function. Now the common base e is a number. It's an irrational number, just like pi, that goes on forever and ever and ever. And this is what e represents. 2.71828818, blah, 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 etc., etc., etc. It is used a lot as a base for exponential functions, just like you see here, e raised to the x. Now, just so that we can get a clear picture of what this is what the graph of e to the x looks like. Now, you'll notice I have some coordinates here. So this is if x is equal to 0, then e to the x is equal to 1. And that's because e raised to the 0 power, anything raised to a power of 0 is 1. Then this point here, 1, 2.718, 1, that's if x is equal to 1, so e to the first, which is just e. And that's why the y value here is 2.718, which is that the first couple numbers of the irrational number e. And then here we have 2, so that means that e raised to the second power, if you raise 2.71828, etc., square it, you would get 7.389, etc., etc., etc. So that's what those coordinates are. Now you'll notice that from this graph on the left side, it does start leveling out. And what I mean by that is that here at y is equal to 0, this is a horizontal asymptote. Remembering that an asymptote is an invisible line that the graph will never cross nor touch, even though it does look like it's touching, if I were to zoom into this graph, we would see that the graph actually gets infinitely close to this line, but it never actually touches. And that's just something to keep in mind. For the course, you don't necessarily need to be able to graph all of these by hand. That's why we're going to use a graphing calculator. But you do need to know at least more or less what the graph is going to look like. What is the basic shape? What are those key characteristics? You'll also notice that this graph increases forever. It's going up to infinity. So remember, increasing, decreasing, things like that, knowing how to use or how to find intervals of increasing and decreasing behavior is very important. So for example, this particular graph is increasing forever. So it would be increasing from negative infinity to infinity. Because even though this is leveling out at, it's going to the left forever and it's increasing forever upwards. Now moving on to logarithms. A logarithm is defined as the power to which a number must be raised to get some other value. So here, this is how you read a logarithm. What this says is log base 2 of 5 is equal to x. Now, a log is the inverse operation of an exponential function. So what this means here, this little number, this is the base. The base is, for an exponential, is that big number here, the number that's being raised to an exponent. So what this means is that 2, right, my base, raised to what number, x, is equal to 5. So that's why I put here this arrow. That's what that logarithm translates to. 2 raised to the x is equal to 5. So logarithms, even though it is the inverse operation, we can always write it as an exponential function, which makes it a little bit easier to solve sometimes. Now, you'll see sometimes ln. ln is another logarithm. The difference here is that ln is called the natural logarithm. And since e is the natural base or the common base, the ln just indicates that the base of the log is e. So instead of writing log base e like I have here of x, we use ln of whatever, x, in this case 3. I use this so we can examine the example. So the ln of 3 is equal to x. If we write that as an exponential function, that means that the base, because this is ln, is e raised to the exponent of something, so in this case x, is equal to that number, which is 3. So if we're trying to figure out what is x, that means that we're trying to find the exponent of e that would give you the answer of 3. So let's look at what the graph of the ln of x looks like. Because this is the inverse of the exponential function, if you remember anything about inverses from last year, it is the reflection along the line y is equal to x. So if you reflect it along that that diagonal line, which is this here, then this will come down like that. And you see how it looks like this graph here. It's going it's still increasing, but it's leveling out eventually. So what we have on this graph, first we're going to start off with the ln of x, which is 1. Now the ln of 1 is always equal to 0. That's why the y value here is 0. Now, if I were to find, so for this coordinate here, 2, 0.693, if I were to do the ln of 2, that means that e raised to what exponent would give you 2, and that is 0.69. Now, just so that you kind of understand that a little better, let me show you here on the calculator. So again, if I were to take e, which is here, and I raise it to the exponent of that number, 0.693, I would expect that it would give me 2, because remember that it is the inverse. And as you can see here, we get 1.9997, etc. But this is a rounded number, so we're not going to get an exact 2. But if I would have round 1.9997, I would get 2. So that's why that's the y value. And then here the ln of 3 is equal to 1.099, and that's because e raised to 1.099 would give you a rounded number of 3. Now, here we had a horizontal asymptote at y is equal to 0, but because this is the inverse, that means that here we have a vertical asymptote at x is equal to 0. Again, I'm just highlighting these key characteristics that we need to keep in mind. And even though this graph is not necessarily going up and up and up all the way up to infinity, like here in this picture, it is increasing forever. It's just leveling out here at the asymptote. So let's say I wanted to find the intervals of increasing behavior. It doesn't go past this x is equal to 0, so I can't say it's increasing forever because the graph never crosses over to the negative x's. So we would say that this is increasing starting at 0, because that's where my vertical asymptote is. And remember, I'm not including it because it's not touching. And also for increasing and decreasing, we never include values. But it is increasing starting from 0 and then forever to the right, so to infinity. So those are just some things to keep in mind about natural log and e. Now, algebraically, we will need to work with these functions, so you do need to know how to use logs and e in order to solve for a particular variable. Now, when we're solving for a variable, you need to apply the inverse operation, which is what we did with our trig functions. It's what we do always when we're trying to solve for an equation. If you have x plus 4 is equal to 5 and you want to solve for x, we would need to subtract the 4. We're applying the inverse of the operation of addition. We are subtracting. So that's exactly what we're going to do here. So this first one, we have 3 ln of e raised to the 4x plus 1 is equal to 11x minus 4. First of all, if you have the ln of e, these are already inverse operations applied to each other. So what happens here is that this cancels out, and we're left with the 3 times what the exponent was, which is 4x plus 1. And that's going to equal to 11x minus 4. So ln and e cancel each other out. So here are some examples of how you can see it. The ln of e raised to the x, these will cancel and the exponent comes down and it equals to x. If you had e raised to the ln of, let's say, 3, e and ln would cancel and you would end up with 3. So that's just how that works, how ln and e cancel each other out, depending on what's the primary function here. So here, since ln and e cancel, this is a much simpler equation for me to solve. I'm going to distribute this 3. So we get 12x plus 3 is equal to 11x minus 4. Subtract the 11x over, and we get x plus 3 is equal to negative 4. Subtract the 3, and we get that x is equal to negative 7. So this would be my answer. Now all of this is fine, and here this one was an easier one because the inverses were already present. Now here we don't have an inverse of this log. We learned that ln and e are inverses, but how do I know how to cancel out an actual logarithm, not the natural log? Well, that depends on the base. Now you notice in this example, we don't have that little number here to tell us what the base is. In order for you to figure out what the base is, because there's no number, if there's no number, it's always 10. So if you prefer to write it in, you can. But typically, when the base of a logarithm is 10, it's never written. So that's just something to keep in mind. Every other number, if the base was 3, you would see the 3. So if there's never a number, then that means the base must be 10. To cancel out the logarithm, what you do is you raise that log, or rather, you turn that logarithm into the exponent. So if the base is 10, that means that 10 is going to be the base and this will be the exponent. So I'm going to apply 10 here as my base, but whatever you do on the left, you have to do on the right. So this will also be 10. So what we have is 10 raised to the log of base 10 of 2x minus 3 is equal to 10 squared. So whatever the base is, you just turn this into an exponential equation. Whenever you have a base raised to a log with the exact same base, those are inverses. That's what happens here. We have the base, and then this is a log with the same base. That's why e and ln cancel. They have the same bases. Like, for example, if I had log base 3 of x is equal to 4, if I want to solve this, I would look at the base, which is 3, and apply that to both sides. So then 3 and log base 3 will cancel, and I get x is equal to 3 raised to the 4th. So that's what we're doing here. 10 with the log base 10 will cancel. This now moves down. It's no longer an exponent. This is 2x minus 3 is equal to 10 squared, which is 100. And now we solve. Add 3 to both sides. We get 2x is equal to 103, and then divide the 2. So x is equal to 103 over 2. And this is fine, right? Something that you're going to hear me say a lot throughout the course is that sometimes our answers don't necessarily look very pretty. 103 over 2, sometimes you'll look at it and be like, that doesn't seem right, because it's like this weird looking fraction. You know, it's not just a number like 4 or 7 or -2, you know, but that's okay. Our answers sometimes look more complicated than the actual question. Now let's look at this one here. We have 2e raised to the 5x minus 6 is equal to 12. If we want to solve for x, we have to first isolate the e. So I'm going to divide this 2 to both sides. And we get e raised to the 5x minus 6 is equal to 6. In order to cancel out e, the inverse operation is ln. So I'm going to apply ln to both sides. ln and e will cancel. This 5x minus 6 is no longer an exponent, and that's going to equal to the ln of 6. Now this is some number. It's a decimal of some kind. If this was a non-calculator question, you are not expected to know what that decimal is. You're just going to leave your answer like that. You're going to leave it as the ln of 6 and don't do anything else. I mean, you're going to solve for x, but you're going to keep that just like that. So we want to still solve for x, so we're going to add the 6 over. Now I can't add these together because this is the ln of 6 plus 6. This is a number, this is a number. We're just going to leave it. So now we have 5x is equal to the ln of 6 plus 6, and then we divide the 5. So this would be my answer. X is equal to the ln of 6 plus 6 over 5. Now over here we have the ln of 4x plus 7 is equal to -3. In order to cancel out the ln, the inverse operation would be e. So we're going to apply e to both sides, making this the exponent. So e raised to ln, remember they cancel. This moves down, so 4x plus 7 is equal to e raised to the -3. And now we're going to solve for x. Remember, we can leave e to the -3. You can also rewrite this if you wanted to or you prefer as 1 over e to the 3rd. If you recall your rules of exponents, which we'll go over after this, Whenever you have a negative exponent, that means it's in the wrong spot. If it was originally a numerator, it would move down to the denominator. If it was in the denominator, you would move it up to the numerator and then change the sign of that exponent. So e to the negative 3, if I put this in as a fraction, it's in the numerator, so I'm going to move it down to the denominator and make the exponent positive. So let's continue here. I'm going to subtract the 7 next. So we have 4x is equal to 1 over e to the third minus 7, and then we divide the 4. So x is equal to 1 over e to the third minus 7 over 4. Or if you prefer to just leave the negative exponent, this is the same thing as saying e to the negative 3 minus 7 over 4. Either one of these, if this was a free response question, would be acceptable. However, if it was a multiple choice question, you have to be able to identify which is the correct answer. So that's why I'm doing both here, so that way you'll know if you see this as a multiple choice option, this is it. But if you don't see it and you see this one, you'll know that it's the equivalent and to select that one. So that's E and ln. Now we're going to review rules of exponents. So this particular slide just has all of those rules with some algebraic examples and then some examples with numbers. We have the product power, the quotient power, the power of a power. So some of these are very familiar or should be familiar. If you have two terms being multiplied that have the same base, then you would add the exponents. If it's being divided, again, it always has to have the same bases. Then you would subtract the exponents. If you have a number raised to an exponent and then that's raised to an exponent, you multiply the exponents. If you have two terms in parentheses raised to the exponent, that means that each of those terms also get raised to the exponent. Same thing with a fraction. You would just apply that exponent to both the numerator and the denominator. This was the rule we just discussed. If you have a negative exponent, that just means that that particular term would move down to the denominator and then the exponent becomes negative. Or if it's a fraction, you would flip the fraction and make the exponent positive. Anything raised to an exponent of 1 is itself, and anything raised to an exponent of 0 is equal to 1. Now, this is calculus, right? So we're going to expand these rules of exponents to radicals. A radical is any expression that is using the radical symbol. Now, most of us know this symbol as the square root symbol. However, there are other radicals. We have the square root, we have the cube root, we have the fourth root, fifth root, sixth root. We have infinite amount of roots. Now, here's an example. This is the cube root of 64. So this little number here, that's called the index, and that tells you what root we're looking for. If you don't see a number there, then that means it's the square root because we don't write that index down. Okay, because that's the very first radical that we look for. A cube root just means that if I were to try to find the cube root of 64, you know, if I were to get the square root of 64, we know this is 8 and 8. The cube root of 64 means that we're looking for 3 identical numbers that would give you 64, whereas the square root is only 2 identical numbers. So a fourth root would mean that you're looking for 4 identical numbers that would give you what's inside the radical. A fifth root is 5 identical numbers that would give you what's inside the radical, etc. So let's say if I wanted to find what is the cube root of 64. That means that I'm looking for 3 identical numbers that would multiply to give me 64. Now I'm not going to use 8 and 8 just because that's the square root, and you can, but just to make it a little bit easier for you to see, 64 can also be broken down to 16 and 4. And then 16 can be broken down to 4 and 4. See, here are my 3 identical numbers. So the cube root of 64 is equal to 4. Now, radicals can also be written with exponents, and those are called rational exponents. And we're going to be doing this a lot throughout the course, so we need to know how to do that. If I have the nth root of a is being raised to the first power. Now, the root here, the index, is the denominator of the exponent, and the power here is the numerator of the exponent. So this is a raised to the 1 over n. Now, if you have the nth root of a raised to some other exponent, we'll say m. Again, m, the power, is the numerator, and n is the denominator. So this could be rewritten as a raised to the m over n. And we do this because in order to simplify expressions, we can apply those same rules of exponents that we saw in the previous slide using these rational exponents. So these are those main rules here, the one for multiplication, division, when you have a power raised to a power, when you have multiple terms, when you have division, and how you would apply those exponents. But it's the exact same thing. If you have two terms being multiplied, you add the exponents. If you have them divided, you subtract. If you have a power raised to a power, you multiply. It's the same thing, except you're applying those rules with fractions. The exponents, rational exponents, are just exponents that are fractions. So please make sure that you know how to add, subtract, multiply, and divide fractions, because that I will not be able to review over and over. So let's look at a few examples of how to simplify, and these are very similar to the ones that you have in your summer assignment. In order to simplify expressions, especially with radicals, it's so much easier if you rewrite it using the rational exponent. So here we have the square root of xy. Remember that a square root, the index is 2. So even though we don't see it, you should know, okay, my denominator of this exponent is 2. This is not raised to any power, so this is translated to xy raised to the 1/2. Remember that this is, if there's no power, it's just 1. Times, here this is the cube root of y, again to the first power. So this is y raised to the 1/3. Times, and then this does not need to be simplified, this is x. This is still not very pretty. We're going to try to simplify this a little bit more. Here we have these two terms that are being multiplied and raised to the 1/2. So just like we saw here in this rule, if you have two terms raised to the exponent, you apply that exponent to both of those individual terms. So this is x raised to the 1/2 times y raised to the 1/2. So that's this part here, times y to the 1/3 times x. Now we want to be able to combine these. This is all being multiplied. So the ones that have the same base, you are going to add those exponents. So we have here 1/2 plus 1. So I'm going to do that up here. In order to add, we need to write this with a common denominator. So this is 1/2 plus, this we're going to put over 2, meaning we multiply the numerator by 2. So 2 over 2. When we add, what we get is 3 over 2. So this is my new exponent. So this is going to equal to x raised to the 3 over 2. Now we're going to do the same thing with the y's. We have y to the 1/2 times y to the 1/3. So we need to add those exponents together. 1/2 plus 1/3. We need a common denominator here, which if I look, it would be 6, because 2 times 3, 6. So I'm going to multiply this fraction here, 3, to the numerator and the denominator, and this fraction by 2 to both the numerator and the denominator. And what I get is 3 over 6 plus 2 over 6, which gives me a new exponent of 5 over 6. So this is y raised to the 5 over 6. So that would be my simplified version of that particular example. Now let's look here. We have 25x to the negative 1, y raised to the 8th, and everything is being raised to the 3 over 2. Now normally we would start inside of the parentheses and simplify what we can. There's really nothing to simplify, so we're going to leave that. But now what we have to do is apply this exponent to everything that's inside of the parentheses. So you have to apply it to the 25, to the x, and to the y. So this is 25 raised to the 3 over 2 times x to the negative 1 raised to the 3 over 2. And then y to the 8th raised to the 3 over 2. And now let's see what happens. Let's start here with this 25 raised to the 3 over 2. We have to be able to identify what this number would be raised to that exponent. In order to do that, for numbers, it's much easier if we convert this back to a radical. The denominator is the root and the numerator is the power. So I'm going to do that up here. So 25 raised to the 3 over 2 is equivalent to the square root of 25 to the third. Now you can choose to either do the square root first and then raise the exponent, or you can do the exponent and then find the square root. I usually choose to apply the radical first and then the exponent because it keeps our numbers small. Versus if you do 25 to the third first, you're going to get a large number. So the square root of 25, that's 5. And now I raise it to the exponent of 3. 5 raised to the third is going to equal to 125. So that's 25 raised to the 3 over 2. So I can replace this with 125. Now here we have x to the negative 1 raised to the 3 halves. We have a power raised to a power, so we're going to multiply those exponents. So this is x raised to the negative 3 over 2. And then here, same thing. We have a power raised to a power. So you have to multiply 8 with 3 over 2. Keeping in mind when we're multiplying fractions. Multiplying fractions, you just multiply numerator with numerator, denominator with denominator. So I can put this 8 over 1. 8 times 3 is 24. 1 times 2 is 2. And 24 divided by 2 is 12. So that is my new exponent. So this is y raised to the 12th. This is an acceptable answer. However, just in case, if you have a negative exponent, remember that we're going to move it down to the denominator if it originally was in the numerator. So we can rewrite this as 125 y to the 12th over x raised now to the positive 3 over 2. So this is another acceptable answer. Now, if we look at this next example here, it looks pretty intimidating in the sense that we have all of these radicals. We have the square root of 9x minus 27 divided by the square root of x minus 3. In order for me to simplify this, I would need to be able to use those rules of exponents. However, I cannot use these rules of exponents because the bases are not the same. In the numerator, the base is 9x minus 27, where in the denominator, the base is x minus 3. However, what I do notice is that if I factor out a 9 from here in this parentheses, then I would have x minus 3. So let's see what happens if I do that. This is going to equal to the square root of 9 times x minus 3 over the square root of x minus 3. I know the square root of 9, so what I can do is I can move that outside of the radical. The square root of 9 is 3, so this is equal to 3 square root of x minus 3 over the square root of x minus 3. So here what happens, these square roots cancel, and I'm left with the answer, which is 3. So this one ended up working out pretty nicely. Now let's just say, for example, that this denominator was not the square root of x minus 3, but the cube root of x minus 3, which you have a question very, very similar to this one in your assignment. Then what would happen is you could still start off this way. What I'm going to do is, this is a new problem, so I'm going to erase this here. So it's still the square root of 9 times x minus 3 over the cube root of x minus 3. We can still move out the 3, and we get the square root of x minus 3 over the cube root of x minus 3. We still have the same bases, but these don't necessarily cancel because the numerator is a square root, the denominator is a cube root. So I'm going to rewrite this using exponents. So this is going to equal to 3 times x minus 3 raised to the 1/2 over x minus 3 raised to the 1/3. Now this is dividing, right? So what we're supposed to do now is subtract those exponents. So I'm going to do that over here. We're going to do 1/2 minus 1/3. In order to subtract, we need that common denominator, which in this case would be 6. So I'm going to multiply 3 here, and then 2 here and here. So this gives me 3 over 6 minus 2 over 6, which gives me 1 over 6. So this is my new exponent. So my answer would be 3 parentheses x minus 3 raised to the 1/6. This is an acceptable answer. However, we can also write this as 3, the 6th root of x minus 3. So either one of these would be correct. Now, last one here. We have 2x raised to the negative 3 over 4 times y, all divided by x raised to the 1/2, y to the 3rd, and then everything is being raised to the 3rd power. Before we go ahead and apply that exponent, we're going to see about simplifying what's inside here of these brackets, which brackets just function the same way as parentheses. In the numerator, there's nothing I can do because these are all different terms, and same in the denominator. So we're just going to apply those rules of exponents for our common bases. So we have here this x to the negative 3/4 and x to the 1/2. So remember, we're supposed to subtract those exponents. You always subtract the top minus the bottom. So I'm going to do that over here. We have negative 3 over 4 minus 1/2. My common denominator here would be 4. So the only thing I would need to do is rewrite this 1/2. So I'm going to multiply by 2 to both numerator and the denominator. And that gives me negative 3 over 4 minus 2 over 4, which would give me a new exponent for x of negative 5 over 4. So let's start writing down what we got. We have 2x to the negative 5 over 4. Now let's look at the y's. We have y to the 1st over y to the 3rd. So we have to subtract 1 minus 3, which gives me y to the negative 2. And all of this now is raised to the power of 3. So now we apply this power to everything in the parentheses. We're going to do 2 to the 3rd times x to the negative 5 over 4 to the 3rd times y to the negative 2 to the 3rd. Remembering to apply these exponents, especially for the x's and the y's, we're going to multiply those exponents. 2 to the 3rd, that's 2 times 2 times 2, which is 8. Then here we're going to multiply negative 5 over 4 times 3. So that would be x. Negative 5 times 3 is negative 15 over 4. And then y, negative 2 times 3 is negative 6. So this is one acceptable answer. However, if we rewrite this using only positive exponents, both the x and the y would move down to the denominator, but the 8 doesn't have a negative exponent, so that stays up in the numerator. So this would be 8 over x to the 15 over 4, y to the 6. and this would be your other acceptable answer. Hopefully you found this video helpful and this review helpful for the upcoming school year, and I'm very excited to start with you guys. See you then.